Hi, my name is Matt. Welcome to Unbearable 73. Now it's time for this week's Science Roundup, or this, well, whatever. You got to figure it out because I'm going to publish it when I publish it. Now, the articles I pick, as usual, they're things I find interesting in science or engineering or tech, for personal reasons. It's not like I think this is the most important thing we've ever discovered, but, And I have my science mascots, Cthulhu and Mechagodzilla, looking over, so they know if they're there watching it, you know it's for real. Now on to the science. First up, we have an article from Just the News entitled "North America's First Industrial Scale E-Fuels Facility to be Built in Texas." Way too many hard consonant words in there. That should be a typo editor editing this thing that I'm reading to you. The company is called Highly Innovative Fuels Global, or HIF. It's headquartered in Chile, and it's built prototype plants in several South American cities. But the first industrial-scale e-fuels plant is going to be built in Bay City, Texas. There's no pictures of the event, but there's details about it in the article. So what are e-fuels? In this case, the e-fuel in question, it's a chemical process that uses wind energy and pulls CO2 out of the atmosphere to make a gasoline alternative. And it's supposedly, according to the article, a one-to-one. So if you get this product and you can put it right in your car, it doesn't need any special treatment or special engines or whatever. So in concept, that's why I'm putting this out there. It's a good idea. If this is the type of thing we can do with science and engineering, which would be better, better than ruining people's lives by making them buy cars that are $10,000 more expensive because of all the additives you have to put in fuel and the special components on the engines to process them and so forth. And it's carbon neutral. It'll pull carbon out of the atmosphere, turn it to gasoline, which we then put back. Now, like a lot of these like environmentally friendly technology, like solar panels or batteries and whatever, I strongly suspect this involves a bunch of other nasty chemicals and supplementary grid electricity used for it. For example, solar panels seem great until you learn the manufacturing process uses a lot of energy, which we need to get from fossil fuels or nuclear plants, and which are good. Nuclear plants are good, and a lot of nasty chemicals. And to be honest, in fact, not to make an aside, but there are a couple other technologies like this, like thermal depolymerization, for example. If we had nuclear power, we could be turning out the massive amount of garbage, animal waste products. Like, people don't realize, for the amount of, say, cows and chicken that we eat and pigs, the amount of waste product from making those animals into meat, all the blood from the animals, leftover physical materials. If we had a nuclear power plant, we could turn all of that into basically oil and then manufacture it into gasoline and plastic and whatnot. That's a proven technology. They have plants that make it work. They were trying to build one in Philadelphia about 10, 12 years ago. But as it turns out, again, the limitation is you need a lot of electricity to do this sort of thing. It's the same thing with water desalination. All of our water problems could be solved, which means we would stop having to wreck the environment with dams, or we could have living out west a lot easier if we had nuclear power plants. Because one of the free things you get with nuclear power is you can use the excess heat that you're using to turn those turbines. You can use it to desalinate water very easily. And basically, build a nuclear power plant, building a couple of desalination plants that are near it are nothing. But again, nuclear power would solve a lot of things. Anyway, sorry about the rant. I want to try to do something about nuclear power update in the next article as a separate video. So let's go to our next article. Okay. Now, next we're going from carbon neutral energy to one of the most energetic events ever to happen on the surface of the Earth that we know about, in articles from Physics Today. 66 million years ago, at what is known as the Cretaceous Paleogene boundary, over 75% of the Earth's species died off in a very short time, and man had nothing to do with it. This was, of course, the most famous or infamous event for the death of the dinosaurs. We found the crater at the Yucatan Peninsula. I'm going to butcher this name. It's known as the Chicxulub crater. Chicxulub, I think, is the closer way to pronounce it. The impact was first proven by the presence of impact quartz from a cometary asteroidal impact. Louis Alvarez and his son Walter Alvarez, they worked on a project. They wanted to do a father-son project because Walter was according to what I read, he was distanced from his father due to a divorce, and his father was one of those scientists, Nobel Prize winning scientists with isotopes and everything, genius guy. And they wanted to do a project, and Walter was a geologist or a geophysicist, so they wanted to examine the impact theory, and they were able to prove it with geology and physics that the impact must have occurred, and had that impact occurred, it must have done the extinction. And paleontologists resisted that because paleontologists have been resisting what I guess you would say sudden changes to evolution for over 100 years. It's a leftover from when they adopted more scientific methods from catastrophism, I think the term was called, which was a biblical orientation type thing. But growing evidence of catastrophes like volcanic eruptions, supervolcanoes, extraterrestrial impacts and all, on the impact on life, there have been at least 5 known mass extinctions caused by impacts, proven caused, They found another evidence for the Cretaceous impact was the presence of an iridium that only comes from comets in a layer over the entire Earth, in the same layer that these impact quartzes were found in. Yeah. So, and the thing is, about this event, they're still discovering and publishing all the known horrific results of this impact in terms of things that killed the 70% of life. Though I read an article maybe 12 years ago, no longer, but 20 years ago, about hypercanes, which are hurricanes that are larger, more devastating than hurricanes. And they would only form from an energy released into the atmosphere from an impact like this. Right? And then there was the humongous amount of sulfur tossed into the atmosphere, which is proven. That comes up in this. By the way, I'll get to it later. There's other chemicals. Turns out that the Chicxulub crater happened to hit a bed of stored carbon monoxide, or I think it was, or one of the two, carbon dioxide or carbon monoxide. It hit at an angle that led an excess. Like, it was not only was this a pocket of it with a higher concentration than normal in terms of the sequestration in the Earth, but it had an angle that released a lot of it, so that further released more materials. That was another scientific article I read. And then there was an article I read about 12. No, this is the 12 or 13-year-old one. That's probably the last issue of Discovery magazine I ever read. About a paper that proved that there were these firestorms that emerged from the impact that kind of swept across North and South America, right? So killing things, burning to ash and all that sort of stuff. And then, obviously, the known effects of hitting the ocean of the tsunamis that were crashing in, traveling worldwide as the wave traveled through the oceans, the crashing into the shores of North and South America, and Western Africa and Europe, as another example. So, despite all the evidence, there's still resistance to the idea that the extraterrestrial impact caused the extinction. Even though the history and scope of such of the extinction of the impact is amazing, So, one idea that the alternative theorists come up with was that a massive volcanic eruption, which we know did occur at the same time in India, and led to the formation of something called the Deccan Traps. And volcanism is an amazing thing. I'll try to find some articles next week for that. Could have caused the extinction instead of this, or contributed to it. So this is what this article is about. Isotopic evidence weakens the role of volcanism in the extinction event. Okay? The whole article is down below. They go into the science of it. But the long and short of it is they examine the sulfur that was ejected into the atmosphere, and it's far more consistent with the material ejected into the atmosphere by an impact event rather than a volcanic event. And this article goes into the details of that. And I find it fascinating when science is done properly that it's a continuous grind that will validate truth regardless of what you think about it, and relentlessly. Same sort of process occurred with Einstein's general theory of relativity, for example, and that'll come up later. So next up, let's go over to an engineering feat that tests science rather than pure science. This is from NASA's website. It's about CAPTSTONE. Okay. The first satellite for CAPTSTONE was due to launch this month. I will have a follow-up in June as to whether it did launch or not, because it's a whole. I don't know if it did in the first couple of days of May. I will find out in June if they actually got it off. It's a small microsatellite the size of a microwave oven. I think they call it a CubeSat or something like that. And CAPTSTONE stands for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. Okay, this satellite in particular tests the navigational capabilities that CAPTSTONE will give, and it's the beginning of the CAPTSTONE project. The details of which are in the article. Again, I could do a whole video about that, but the goal of this is to get you to read some articles. So, and why is this in particular? Well, this satellite is being sent in what's called a rectilinear halo orbit, or NRHO, and that's an elongated orbit over a normal orbit. You can see kind of what's going on there, but if you had like the Earth, if you can see it, and the Sun, the Earth and the Moon, right, although they're small, an orbital orbit's kind of a small ellipse around one of them, right? This orbit's going to stretch so it hits a particular point of balance between the Earth and the Moon. Right. Now let's go on to our next article, and this is a little more conceptual, but important, okay? This is in a more exotic area of science and engineering right now, but this stuff fascinates me because I love the whole area of computers and electronics and the super science behind them. This article comes from Physics World, and it's about negative capacitance. So, to understand negative capacitance, let me give you a little rundown on capacitance, okay? So, capacitance is one of the fundamental properties of a device, let's say, okay? And it arises when you take two non-conductive surfaces, right, that are not physically connected. Because they're physically connected, you have one object. So they have to be two discrete objects. They're non-conductive, and they're surfaces. They could be straight. They could be curved, right? They could be one ball inside, they could be a ball inside a sphere, right? There could be any, but as long as there's two surfaces, and it doesn't have to be equidistant, but that makes the math involved wonky. But if they're equidistant, it's pretty easy. And if they're non-conductive, right, and you put a voltage difference in them, so the voltage hitting one surface, let's say it's 10 volts, and the voltage on the other surface is not 10 volts, you create a difference of potential, a voltage difference, right? When you do that, the electromagnetic properties start storing energy from the higher voltage in the space between the two surfaces as energy. And the measure of that is called capacitance. And the equation you see on the screen there is Q equals CV. V is voltage, C is capacitance, Q is the potential, potential. The Q is, I'm sorry, C is the constant of proportionality, and Q is the potential capacitance. Okay, sorry about that. Anyway, so what that first equation tells you is, as voltage increases, so will capacitance. So as V goes up, Q goes up. That's the important part of there, right? So the more voltage the more voltage potential difference you have, the more capacitance you have, the more energy can be stored, right? We'll call that positive capacitance, right? So what is negative capacitance? Well, since normal capacitance increases with voltage, and therefore negative capacitance is when you decrease the voltage, but the amount of energy stored increases, okay? And that's a peculiar thing. The article goes into the details about how Professor Salahuddin did this, and honestly, I understand it because I've had to do a little. I never finished my science degree. I intend to, even though I'm getting older. But I remember a lot from my electronics training. Some of it, I had to do some research on what some of the stuff meant. But if you're into this sort of stuff, it's worth reading. And this article is in particular, it's about the creation of a transistor that exploits negative capacitance for the gate voltage. The gate voltage is one of the voltages on a transistor that controls what it does, basically, to keep it simple. I don't want to bog this down in microelectronics, okay? And what it does is that voltage could be 30% lower to obtain the same effect, okay? So now imagine the CPU inside my computer right now has, I believe it's billions of transistors at this point. I can look it up. I know we hit hundreds of millions of transistors in CPUs 10 years ago, okay? So imagine all those billion transistors using 30% less voltage and multiply that by billions of chips around the world. And you can see the power saving that this potential could do. But again, we're in the theoretical phases of it now, even with the engineering. So you just got to keep that in mind. I do talk a bit about this later in another way. I'll bring it back up then. So let's go on next article. This we're still in experimental super science here, and in Michigan, a decade-long project to build a facility for rare isotope beams, abbreviated FRIB, F-R-I-B, at Michigan State University is complete as of May 2nd. This particular particle accelerator, say that 3 times, people, will cost slightly less than $1 billion. In the scheme of science, that's nothing. You know, I think the federal government spends more on toilet paper than that. This facility will produce rare isotopes significantly faster than any other facility currently in existence or projected to be in the next 5 or 10 years. In the long run, this sort of research advances multiple areas, but in particular, it explores and or validates high-end theoretical physics, and it leads to advances in materials science and engineering. The fantastical materials of today's particle accelerator are the everyday materials 100 years later. Now, you might be saying, well, I won't be alive in 100 years, blah, blah, blah. But if we don't do this now, our descendants, whether they're personal descendants or the society, won't have access to the materials they need to continue advancing the state of things. Yeah. So let's go to our next article. Now, from the fringes of super science to science which provides evidence of an event from the distant past. This is from Science News. It's an article about ancient zircons possibly revealing the emergence of plate tectonics. Let me get rid of that capacitance article so you can see what I'm talking about. There we go. Okay. So, with this particular discovery, a large piece of how the inner workings of the Earth function were put in place. But one question's kind of always been, when did the great grinding of plate tectonics begin? Like, when did it start? They've always been looking for some sort of evidence that, which could point to the beginning of this. But again, this is like 4 billion years ago. It was called the Hadean era, right? And there's very little evidence that would survive all the molten activity and the grinding and the crushing, right? Well, let's talk about zircons. I have a link to the Wikipedia about zircons below along with this article, so if you want to read in depth about them, they're a fascinating substance. Zircons are minerals based on silicon that are common in the crust of the Earth. They kind of grow like crystals. If you cubic zirconia, have you heard that term before? The gist of what's needed to understand is that there are a lot of them. There are many different types, and they as they grow, they grab and absorb other materials. Okay, so it's an easy resource to gather in general, but obviously, to gather the zircons from the Hadean era, there were only a few places on Earth. They found another one, right? Okay. So they're easy to gather because there are a lot of them when they're created, even though the area where you might be able to get older ones is rare. When you get there, there's a lot of them, right? But conversely, they are very tiny and they're often composed of chemicals with very delicate chemical structures, which make them difficult to examine by the means we have. But they last for billions of years, okay? This research had given geologists insight into the Hadean era, as I mentioned, which was 4 billion years ago. So as the zircons grow into these crystals, they can capture other elements like uranium, but they tend to exclude elements like lead or, for example. Now, why is that important? Well, because of radiological decay. Ultimately, everything radiological, as far as I understand, I could be wrong on this one. I mean, I know everything decays. I think it all eventually becomes lead because of the way the stabilization works on the radiological decay. Lead's the most stable non-radiological element that they wind up as. And since the zircons tend not to absorb lead at all, but very readily absorb uranium, any lead present in the zircons should be signs of the half-life of the uranium that was in it, so you can date them fairly precisely. Meaning in terms of, like, it was 4 billion years ago, not 3 billion years ago. Not like, it was last Tuesday type of precisely. Right? So, again, why is this important? Well, understanding how the Earth works will eventually produce real models of how the planet and the atmosphere work. I want to get into the whole environmental issue and whatnot. This, like I said, we need more data and more actual science on how things work to make better choices. Which doesn't mean we shouldn't do better by our environment. We should have more nuclear power and get rid of all this fossil fuel stuff, both for the health of the environment and to stop spending money, giving money to places like the Middle East, Russia, or the Ukraine. All of them. Stop buying their oil, build nuclear power plants, like France did, by the way. So let's go on to our next article. And now we're going back to the current day and up in the sky. I mentioned last week that the James Webb Space Telescope had completed its optical alignment and was moving forward in the final phase where the James Webb Space Telescope team and the instrument teams were testing and calibrating the 4 scientific instruments. Each of those 4 instruments can be like dozens or hundreds of other instruments when you configure them. So, and the mirrors are in the process of slowly cooling off to their final operating temperatures in preparation for the thermal stability test. This article is an interview with Erin Smith, the Webb Deputy Observatory Project Scientist. She describes this thermal stability test in detail, and that's in the article there. And then staying in space for our last article, but we'll go into the theoretical high end. We have Stanford's Theoretical Gravity Telescope. This article is from SciTechDaily. In order for engineering to eventually make something experimental, and material scientists, experimental scientists and material scientists have to establish the principles of the actual materials themselves before the actual functional engineers can make everyday products. But in order for those scientists to do, the experimental scientists and the material scientists to do anything, you need theoretical scientists to operating on the fringes of super science, I guess you would say, to come up with a working concept of something. Like, as an example, before I get into the gravity telescope, a more recent example you might have heard of is the Memristor. Throughout the 60s, the concept of what a Memristor was being developed. And in 1971, Leon Chua developed and named the 4th theoretical component of electronics, along with the resistor, capacitor, and the inductor. He called it the Memristor. Now, you've heard me mention capacitor before, a capacitance before. A capacitor is a device that exploits capacitance to store energy in. All right. An inductor is a device that exploits inductance, and usually in the form of a coil, to do the same thing. A resistance is a physical device that resists the passage of energy through it, the voltage, and therefore takes a load, for example, and any voltage that drops across a resistor will eventually dissipate its heat, right? Well, the Memristor is the 4th component of that basic that all electronics are made from, right? So now that was 1971 when Leon Chua codified it and named it, right? In 2007, after decades of research, Hewlett-Packard scientists R. Stanley Williams, well, not that he was doing all the decades, there were multiple scientists, but he was one who made the announcement and the breakthrough. He reported that the development of an experimental solid-state Memristor. So that was 71, 81, 91. So that was about 20, almost 30 years later, right? Now, 10 or 15 years after that, scientists and engineers have begun to experiment using them in prototypes. I remember something about a artificial kind of neuron on a chip with thousands of memristors. I know Intel's trying to develop some sort of memory technology based on it. I heard something about last year about that I'll see if I can find that for next week. So this model of the gravity telescope is the same kind of concept. The conceptual image produced by this gravity telescope, and I'll see if I can, let me lower this so you can see it a little better. Okay, is 1,000 times, will be 1,000 times more precise than the strongest imaging technology in use today. They created this to look for and more closely examine exoplanets. Like exoplanets are planets outside the solar system. This solar system, they've discovered, I believe it's over 5,000, maybe over 10,000 by now. And they usually do it by either detecting the effects of the exoplanet via gravity on its star, or on the light that comes from the star, right? And so they can kind of calculate where it is. But this telescope will actually allow you to see the exoplanets, and get images of them, because it will be 1,000 times more precise, right? Now, this technique, and way back to I mentioned Einstein before, this technique framework uses gravitational lensing, right? And this gravitational lensing is something Einstein predicted, which they eventually were able to measure years later, which further validated his theory of general relativity, right? So the short script of the technique, the scientists create a model where they can use solar gravitational lensing by positioning a telescope with respect to the sun and the exoplanet they're aiming at, or where they're looking for one. And because the bits of light that are coming from the exoplanet will be, the trajectory will be altered by the sun, they can use that to basically resolve a much higher image. Okay? Now, the reality is that due to the limits of human lifespan and the level of technology that we're likely to achieve in the next 500 years, the vast majority of us humans will never be able to visit even the moon. But it's awesome stuff like this concept, the James Webb Telescope, with the older Hubble Telescope, that kind of lets us at least get our minds out there and see some amazing stuff, right? So, well, that's it for this weekend. This week's round of articles I wanted to share. We've managed to we'll keep inspiring you all. We'll also never be able to build cool stuff like the Death Star or the Daleks or even Godzilla. So, comment down below if you have any questions, or any areas you want me to look for articles for in the next video. Share your thoughts. Share this video if you enjoyed it. Like if you like. Dislike if you dislike. Subscribe if you want to hear more from me. My name is Matt. This has been Unbearable 73. Have a nice day, and I am out of here.